Today's topic is canonical ensemble and condition of thermal equilibrium. An ensemble in which there are large number of independent identical systems having same temperature T, same volume V and same number of particles N is called canonical ensemble. So canonical ensemble is a group of identical systems having same values of T, V and N, having same values of temperature T, volume V and number of particles capital N. In this ensemble, each system is isolated from others by rigid, conducting and non-permeable walls, and total energy of all the systems remains constant. These systems can exchange heat mutually through conducting walls. So these systems are separated by conducting walls so that their temperature T remains same. Equilibrium state is the most probable state. We determine condition of maximum probability under the given restrictions. Restriction is this, that total energy is constant. Let two systems of energy E1 and E2 are in thermal contact and their total energy E1 plus E2 equal to E, which is constant. So we are considering two systems in thermal contact with each other. Energy of first system is E1 and energy of second system is E2. And we have the condition that total energy is constant. So we assume E1 plus E2 equal to E, which is constant. From the postulate of equal a priori probability, probability for first system having energy E1 is given by P E1 equal to C1 omega E1. Here C1 is a constant and omega E1 is the number of microstates for first system at energy E1 in very small energy range dE. So if omega E1 is the number of microstates at energy E1 in very small energy range, then PE1 probability will be proportional to this omega E1. It is proportional to the number of microstates. So PE1 equal to a constant C1 times omega E1. Similarly, probability of second system having energy E2 is given by PE2 equal to C2 omega E2. C2 is also a constant and omega E2 is the number of microstates for second system at energy E2 in very small energy range dE. So PE1 is C1 omega E1 and PE2 is C2 omega E2. These are the two probabilities. For PE1 is probability for first system having energy E1 and PE2 is the probability for second system having energy E2. Now the combined probability of having energy of first system E1 and that of second system E2. This combined probability we write by P E1 E2 and it will be equal to product of about two probabilities. P E1 E2 will be equal to PE1 into PE2. This is the combined probability that first system have energy E1 and second system have energy E2. If we substitute the values of PE1 and PE2 from these equations 2 and 3, then we have PE1 E2 equal to C1 C2 omega E1 omega E2. PE1 is C1 omega E1, PE2 is C2 omega E2. Now we take the log, then log PE1 E2 equal to log C1 plus log C2 plus log omega E1 plus log omega E2. And now we differentiate it with E1. Differentiating with E1, we have delta upon delta E1 log PE1 E2 equal to delta upon delta E1 log omega E1 plus delta upon delta E1 log omega E2. Now in this second term, it is the differentiation of log omega E2 and differentiation is with respect to E1. Now we make this differentiation with respect to E2. So we multiply and divide by delta E2 so that this second term will become delta log omega E2 upon delta E2 into delta E2 upon delta E1. And now we will find the value of delta E2 upon delta E1. For this we use this equation 1, which is E1 plus E2 equal to E, that is constant. We differentiate this equation 1 and get delta E1 plus delta E2 equal to 0. E is constant, its differentiation is 0. So this gives delta E1 equal to minus delta E2 or delta E2 upon delta E1 equal to minus 1, and put this value of delta E2 upon delta E1 in this equation. Here delta E2 upon delta E1, we put it as equal to minus 1. Then we get P delta upon delta E1 log P E1 E2 equal to delta upon delta E1 log omega E1 minus delta upon delta E2 log omega E2. Now in equilibrium state, probability PE1 E2 will be maximum, and then left hand side of above equation vanishes. We want to find the condition of thermal equilibrium. Condition of equilibrium is one for which probability is maximum. Most probable state is the condition of equilibrium state. So in thermal equilibrium, in equilibrium state, probability P will be maximum, log P will be maximum, so its differentiation will be equal to 0. So left hand side is equal to 0, and so we have right hand side equal to 0. If we put this right hand side equal to 0, then delta upon delta E1 log omega E1 will be equal to delta upon delta E2 log omega E2. This is when we put right hand side equal to 0, delta upon delta E1 log omega E1 minus delta upon delta E2 log omega E2 equal to 0. This gives delta upon delta E1 log omega E1 equal to delta upon delta E2 log omega E2. So according to statistical mechanics, necessary condition for two systems in thermal contact to be in thermal equilibrium is that value of the function delta upon delta E log omega E must be the same in two systems. From this equation 6, we conclude that the value of the function delta upon delta E log omega E must be same for two systems. If we put E equal to E1, then we get the value of left hand side, and if we put the value of E equal to E2, then we get the value of right hand side. So we see that this function delta upon delta E log omega E must be same for two systems. This function we write it as beta E. It is function of E, energy. So beta E is equal to delta log omega E upon delta E, or we can write it as 1 upon omega E delta omega E upon delta E. From equation 6 and 7, this is equation 6, delta upon delta E1 log omega E1 equal to delta upon delta E2 log omega E2, and this is equation 7, beta E equal to delta upon delta E log omega E. If we put delta upon delta E log omega E equal to beta E, then in equation 6, left hand side will becomes equal to beta E1 and right hand side will becomes equal to beta E2. So condition for thermal equilibrium will be this beta E1 equal to beta E2. So this function beta must be same for two systems when they are in thermal contact. This is the condition of thermal equilibrium for two systems in thermal contact with each other. Now we see this function beta E, which is delta log omega E upon delta E. Dimension of beta is inverse of dimension of energy. This is beta. Log omega E is dimensionless. Omega E is the number. It is the number of microstates. So it is a number. Log omega E is dimensionless quantity. So dimension of beta will be equal to 1 upon dimension of energy. Delta E have dimension of energy. So dimension of beta is inverse of dimension of energy. We know that when two systems are in thermal equilibrium, their temperature remains the same. Now according to statistical mechanics, if temperature of two systems are same, value of function beta must be same for those two systems. So we write following relation between function beta and temperature T. So when two systems are in thermal equilibrium, their temperatures are same, and we have found this condition that the value of beta will also be the same. So we write beta, we relate beta with temperature T in this way. We write beta equal to 1 upon Kt. Kt have dimension of energy because beta have dimension of 1 upon energy. T is absolute temperature. Then this constant K in Kt is, it have dimensions of energy upon temperature. Kt have dimension of energy. So dimension of K equal to dimension of energy upon dimension of temperature. So it is having dimension of energy upon temperature, and unit have its unit is joule per degree Kelvin. This constant K is known as Boltzmann constant. Now we consider the next topic. Question is, define entropy on the basis of statistics. Establish relation between entropy and thermodynamic probability. First we see statistical interpretation of entropy. Entropy is a measure of disorder of a system. With increasing disorder, entropy increases. So entropy is a measure of disorder of a system. When disorder of a system increases, its entropy increases. Since most probable state which have maximum thermodynamic probability. Thermodynamic probability is number of microstates. Most probable state is one which is having maximum number of microstates. So most probable state having maximum thermodynamic probability, it is a state of maximum disorder. Entropy will be maximum in the state of maximum thermodynamic probability. So when thermodynamic probability is maximum, probability will be maximum, and it is the equilibrium condition, and in that case, in this case the entropy will be maximum because disorder will be maximum. So most probable state having maximum disorder, maximum probability, and maximum value of entropy. On this basis, Boltzmann established relation between thermodynamic quantity entropy and statistical quantity thermodynamic probability. Entropy S is thermodynamic quantity, and thermodynamic probability, which we write by W, it is statistical quantity because it is number of microstates. So thermodynamic probability W, it is statistical quantity, and entropy S, it is thermodynamic quantity. We find the relation between these two quantities. Relation between entropy and thermodynamic probability. According to Boltzmann, entropy S is a function of thermodynamic probability W. So we write S equal to Fw. As we see, when W is maximum, thermodynamic probability is maximum. It is the most probable state or equilibrium state. So it have maximum entropy because disorder is maximum in this state. So as W increases, S increases. So we write S as a function of W. To find the nature of this function F, we consider two systems in which value of entropy are S1 and S2, and value of thermodynamic probability are W1 and W2 respectively. So we have S1 equal to Fw1 and S2 equal to Fw2. For first system, we write S equal to S1 and W equal to W1, and for second system, we write S equal to S2 and W equal to W2. So from S equal to Fw, we have S1 equal to Fw1 for first system and S2 equal to Fw2 for second system. Now combined entropy of two systems will be equal to S equal to S1 plus S2. If entropy of two systems are S1 and S2, then combined total entropy of the system will become S equal to S1 plus S2. And combined thermodynamic probability for two systems, it is W1 into W2. We write combined thermodynamic probability by W. So W is equal to W1 into W2. So we have combined entropy S equal to S1 plus S2 and combined thermodynamic probability W equal to W1 into W2. In entropy, we added these two entropies, and in thermodynamic probability, we multiplied these two thermodynamic probabilities. Substituting the values of S, S1 and S2 from equations 1, 2 and 3 respectively in equation 4, we have equation 4 is S equal to S1 plus S2, and we put in this equation the values of S, S1 and S2 from previous equations. S is equal to FW, S1 is equal to FW1 and S2 equal to FW2. If we put these three values here, S equal to S1 plus S2, then we get FW equal to FW1 plus FW2. And now we put the value of W. W is equal to W1, W2. If we put this value here in FW, we have FW1, W2 equal to FW1 plus FW2. Now differentiate this equation, equation 6, partially with respect to W1 and W2. We write this as equation 6, and if we differentiate this equation partially first with respect to W1, then we get W2 F dash W1 W2. Differentiation of FW1 W2 is F dash W1 W2. F dash represent the differentiation. And if we differentiate with respect to W1, then from W1 W2 we get W2. So differentiation with respect to W1 gives W2 F dash W1 W2, and in right hand side we have F dash W1. It is the differentiation of FW1 with respect to W1, and differentiation of FW2 with respect to W1 is 0. Similarly, if we differentiate this equation with respect to W2, then we get W1 F dash W1 W2 equal to F dash W2. Dividing equation 7 by equation 8, these two equations are equation 7 and equation 8. If we divide these two equations, then F dash W1 W2 will cancel out, and we get F dash W1 upon F dash W2 equal to W2 upon W1. Or we have W1 F dash W1 equal to W2 F dash W2, and we write these two equal to K. So we have now two equations. First is F dash W1 F dash W1 equal to K, and second is W2 F dash W2 equal to K. From first equation we have F dash W1 equal to K upon W1, and from second equation we have F dash W2 equal to K upon W2. If we integrate F dash W1 equal to K upon W1, then integration of F dash W1 will give FW1. So FW1 equal to K, and integral of 1 upon W1 is log W1. So we have FW1 equal to K log W1 plus C. C is constant of integration. Similarly, if we differentiate this second equation, if we integrate this second equation, F dash W2 equal to K upon W2, then we get FW2 equal to K log W2 plus C. And in general, from these two equations we can write that FW equal to K log W plus C. If we have W equal to W1, then we get FW1 equal to K log W1 plus C. If we have W equal to W2, then we have relation FW2 equal to K log W2 plus C. So above two equations can be written in general as FW equal to K log W plus C. And FW is entropy S, so we have the relation S equal to K log W plus C. This is the relation between entropy S and thermodynamic probability W. C and K, these are two constants which we have to determine. First, we will determine the constant C. Value of constant C can be determined by using Nernst heat theorem, third law of thermodynamics, according to which if absolute temperature of a system tends to 0, if temperature T becomes 0, then entropy will tends to 0, S tends to 0. If capital T tends to 0, S tends to 0. So at absolute temperature, when absolute temperature becomes 0, entropy S also becomes 0. In this case, thermodynamic probability of a system tends to 1. In this case, W will becomes equal to 1. So when T becomes 0 at absolute 0 temperature, T cannot be equal to 0. So we write T tends to 0. In this case, entropy S tends to 0 and W tends to 1. The system will remains in only one state. So thermodynamic probability W is 1. Since at absolute 0 temperature, only one orientation of system is possible. So when W tends to 1, S tends to 0, if we write these two values in this equation, we write W equal to 1 and S equal to 0, then log 1 is 0, and this will give the value of constant C, which comes equal to 0. So constant C is 0, put this value in this equation, then we have S equal to K log W. Now this is the relation between entropy S and thermodynamic probability W. Now we have to find the value of this constant K, determination of constant K. For this we consider 1 mole ideal gas at pressure P1 and volume V1. Let its pressure change to P2 and volume change to V2. V2 is greater than V1, and this is changed by isothermal expansion. We are considering isothermal expansion of 1 mole ideal gas. In this expansion, V1 becomes V2 and V2 is greater than V1. So we consider a vessel of volume V2, and first we consider that 1 mole ideal gas is inside this vessel in a small volume V1. V1 is less than V2, vessel is of volume V2, and gas is restricted in a small volume V1 initially, and then if it expand by isothermal process, then initially it is in volume V1, so probability of finding a particle in volume V2 will be equal to V1 upon V2. Correct this. Probability of finding a particle in volume V2, it is volume V2, write V2 in place of V1. So the gas is initially in volume V1 and total volume is V2. So probability of finding one molecule in volume V1 is equal to V1 upon V2, and in 1 mole gas there are n molecules, n is Avogadro number. So probability of finding these n molecules in volume V2 will be equal to V1 upon V2 to the power n. So total volume is V2 and gas is confined in volume V1. So probability of finding a one molecule in volume V2 is V1 upon V2, and if we have n molecules, then probability of finding these n molecules in volume V2 will be V1 upon V2 to the power n. We write this thermodynamic probability by W1. And when this gas expand isothermally by isothermal process, now the volume becomes V2. Total volume is V2 and gas is in entire volume V2. So the probability of finding the n molecules now will be equal to V2 upon V2 to the power n, which is 1. This thermodynamic probability we write by W2. So initially thermodynamic probability is W1, it is V1 upon V2 to the power n, and finally it is W2, which is equal to 1. Now we find the change in entropy by using this relation S equal to K log W. Change in entropy delta S is equal to S2 minus S1. S2 is final entropy and S1 is initial entropy. So S2 is K log W2 and S1 is K log W1. Now put the values of W2 and W1. Then this change in entropy delta S will becomes K log 1 minus K log V1 upon V2 to the power n. Log 1 is 0. So this becomes equal to minus K log V1 upon V2 to the power n, and this will becomes equal to minus Nk log V1 upon V2, and we write it as Nk log V2 upon V1. So change in entropy comes out to be equal to Nk log V2 upon V1. From thermodynamics, we know that in isothermal expansion of ideal gas, in which volume of 1 mole gas changes from V1 to V2, change in entropy delta S comes out equal to R log V2 upon V1. If we compare these two values of delta S, in thermodynamics we get it equal to R log V2 upon V1, and here we find it as Nk log V2 upon V1. If we compare these two equations, then we get this relation Nk equal to R, and this gives the value of constant K. It is equal to R upon N. R is universal gas constant and N is Avogadro number. If we put these values of R and N, then value of K is found equal to 1.38 into 10 to the power minus 23 joule per degree Kelvin, and it is known as Boltzmann constant. So this is the relation between S and W. S equal to K log W, and K, the constant here, is Boltzmann constant. So this is the relation between entropy S and thermodynamic probability W. S equal to K log W.